Department of IHPT, MJ Medical College, Indore. Today I am going to do a presentation on the topic quality control in TTI. The moderator for today's seminar is Dr. Ramuthaku sir, Associate Professor, Department of IHPT, MGM, Indore. Before going into the topic proper, I want to give an overview about quality control and TTI and what we are doing in our department. So quality control is management of testing process. It includes assessment of the accuracy and reproducibility of a test. Equipments or instruments used to perform tests must be monitored to determine if they are functioning properly. Reagents must be tested to determine if they have maintained their specificity and sensitivity. And it also includes quality control of the components which we make. TTI. So, what is transfusion transmissible infection? A pathogen should have the following characteristics for labeling as a transfusion transmissible infectious agent. It should be asymptomatic or cause subacute infection in the donor. It should have a long incubation period for the development of symptoms. It should be able to live, persist, or recur in donor and recipient population. It should be stable in stored blood and components at various temperatures. It can have a latent phase via microbial nucleic acid incorporation into the blood cells of the infected host. The microbial nucleic acid can reactivate to initiate infection in the recipient when transfused with blood from an infected donor. So quality control in TTI. A quality-oriented approach is essential for TTI screening in blood bank in order to provide safe and effective product at all times. As per the Drugs and Cosmetics Acts of India, mandatory tests for screening of blood donation include anti-HIV 1 and 2 antibodies, anti-HCV antibodies, hepatitis B surface antigen, Treponema pallidum, and malaria. Commonly used screening tests are rapid diagnostic test, ELISA, chemiluminescence, and NAT. So the type of rapid assays are, most common types are immunochromatographic assay or lateral flow, which we commonly use for the rapid test which we use in our department. The other three are immunoconcentration or dot plot assay, which is a solid phase immunoassay where antigens are immobilized on a porous membrane. Antibodies, if present, bind to these immobilized antigen and produces a distinct colored dot against a white background. The other thing is dipstick and combined assay based on enzyme immunoassay. This uses a chemical impregnated pad to detect analytes in a liquid sample. And the other one is particle agglutination, where it detects antibodies or antigens in a sample by looking for clumps of antibody coated particles. So these are the rapid tests which we use in our department. For malaria, we use EZIT. For syphilis, we used from the company Recombigent. For HCV and HPS AG, we use from Kosh Bio. And for HIV, we use it from Biogenics. So this is what the principle behind the rapid test which we are doing. This is immunochromatographic assay, which is a lateral flow. So from this diagram we can see this is a sample pad there and here is our conjugate pad. In this conjugate pad we have the antibodies which we coat with some substances like which the company might have coated with some substances like gold, latex or fluorophos. Any substance can be there, but it will be coated with the antibodies. And here we have the nitrocellulose membrane and here we have the test line antibodies and the control line antibodies. This control line antibodies will already be coated with IgG antibodies, it will be there. So whenever we put the analyte, that is the substance which we want to diagnose, we will just put the analyte here in the sample pad and it will go to the conjugate pad. In the conjugate pad, there occurs antigen antibody reaction and it will flow through a capillary flow in this nitrocellulose membrane. And this is a porous membrane so that the movement can occur. And here we will get the results. If in both the test line and the control line, we get the lines or the something which we can detect here, then it means that the result is positive. Graphic paper by capillary action. So this I took it from NACO 2015 guidelines. This is how we are going to interpret the immunochromatographic test for rapid assay. Here the control should always be positive. Whenever we get a result, if we get positive in any one of the result also, the control should always be positive. Then only we can take this as a reliable result. So here the control is also positive, and HIV1 and HIV2 also there is line. So this is reactive for both HIV1 and 2. And here HIV2 is positive. This is reactive for HIV2 positive. Here we can see only in HIV1 line is there, but in control there is no line, which means the test is not valid because the control is not giving positive. Then that means the test is not valid. So here again this is positive for HIV1 and this is negative. Since both HIV1 and 2 there is no reaction, this is negative, and this again control may there is no reaction, so this is invalid again. So what quality control are we going to look for in this rapid test? The external controls, which we'll see in the further slides. The external controls, which should include both positive and negatives, should be incorporated along with every batch of 15 samples or on daily basis in case the turnover of samples is more than 15. The kit should have minimum shelf life. Whatever kit we have, the rapid kits we have, those kits should have a minimum shelf life of 5 or 6 or 12 months, whichever is more, at the port of discharge. The time required for performing those rapid tests should not be more than 30 minutes, and the control dot or band should be able to detect the presence of human immunoglobulins and should not be just a procedural control or meant for merely checking the flow of reagents or integrity of the antigen. The rapid assays which we do should have sensitivity of 100% and specificity of more than or equal to 98%. So from Central Drug Standard Control Organization, it is stated that rapid test approved by CDSCO shall be used for screening in an emergency in rural areas or any center collecting small volumes or where power and equipment maintenance is a problem. Only in these cases they have approved for the use of rapid test. According to DGHS and NBTC standards 2022, small centers which do not have provisions to do ELISA or chemiluminescent assay may release blood after rapid test. However, the important point is rapid test is not recommended and every effort should be made to shift to ELISA or CLIA test. Moving on to ELISA, I'm just giving an overview of the steps done in ELISA. ELISA is based on the measurement of an enzymatic reaction associated with immune complexes. This is the simplest form of the steps. First, there is adsorption of antigen or antibody to a plastic solid plate, followed by addition of unlightened test samples. We are going to incubate the reactions. We are going to separate the bound and free reactants by washing. Then we are going to add a enzyme conjugate, and we are going to add a substrate for the color development, and we are going to read the assay. So these are the ELISA tests which we use in our department. For HIV, we are using Herba ELISA. For HCV, we are using Aventar microbial ELISA. For HPS AG, we are using Herba ELISA. So this is an overview of the different types of ELISA. In direct ELISA, there is an antigen coated well. In direct and indirect ELISA, we have an antigen coated well. To this, in the direct ELISA, we are adding enzyme conjugated antibody which is to be measured, and we are going to add a substrate and we are going to measure the color. This is direct ELISA. Here we are using only one antibody. What we want to know, that antibody we are adding. This is direct ELISA. In indirect ELISA, we are going to add antibody to be measured without adding any conjugate to it. The antibody which we want to measure, we are not going to add any conjugate to it, but we are going to add a secondary antibody which is conjugated. So here there are two antibodies, the antibody which we want to measure and another secondary antibody which we have conjugated. In direct ELISA, we have directly conjugated the antibody which we want to measure. In indirect, we are going to add a secondary antibody which is conjugated, and we are going to add a substrate and we are going to measure the color. In sandwich ELISA, here there is an antibody coated well. The previous two, it was antigen coated well, and here this is the antibody coated well, and we are going to add the antigen which we want to measure. And now we are going to add a secondary enzyme conjugated antibody. So the antigen and antibody is sandwiched between the secondary antibody. That is why it is called a sandwich ELISA. the antigen and antibody, it is sandwiched in between the enzyme conjugated secondary antibody. Then we are going to add substrate and we are going to measure the color. This is sandwich ELISA. Cooperative ELISA, we are going to incubate the antibody and antigen before we want to measure it. Then we are going to add it to the antigen coated well. Then we are going to add the secondary antibody, which is enzyme conjugated, and then we are going to add substrate and we are going to measure the color. So the most commonly used are direct and indirect ELISA. Again, there will be antigen coated wells, and in direct ELISA, we are just going to add the antibody to be measured with the enzyme conjugate with it, and we are going to look for the signals, what it is going to give, if it is positive or negative. But in indirect ELISA, we are going to add the primary antibody to be detected, and we are going to add a secondary antibody with enzyme conjugate to it, and we are going to measure if it is going to give positive or negative by adding substrates. So now moving on to the topic proper, implementation of quality control for TTI. So these are the steps which we have to follow for maintaining QC in TTI. The steps are, we have to establish written policies and procedures, design forms and flowcharts, select high quality controls, perform statistical analysis of those controls, set target values, mean and standard deviation, establish Levy Jennings charts, routinely plot control data, establish and implement troubleshooting and corrective action protocols, establish and maintain system for documentation, and train all staffs. We are going to see each point in detail. So establish written policies and procedures. So what we should know. Blood bank should define policies and procedure for TTI screening on blood samples collected at the time of donation itself. The basis for any quality system is that procedures are documented, monitored, and recorded. Procedures should also include correct labeling to ensure correct identification throughout the screening process. Blood bank should also have appropriate systems for linking all test results so that donors' records can be reviewed each time they come to donate. Correct results must be alerted to each donation to prevent errors which might result in transfusion of an unsafe unit. So in our blood bank, this is the donor questionnaire. Here in point C, we have mentioned those points. That is, my blood will be tested for hepatitis B, hepatitis C, malarial parasite, HIV, AIDS, and venereal diseases, in addition to any other screening test required to ensure blood safety. So we have already obtained consent from the donor for all these tests. This is the basic step we have to do, and we are doing it. We have to have SOPs also. The standard operating procedures for TTI lab should be developed in the blood bank as a set of instructions to be followed by all staffs at all times. So the SOPs which we need here are reception and handling of samples, performing the assay, use and maintenance of ELISA washer, use and maintenance of ELISA reader, use and maintenance of pipettes, issuing the results, retrieving and disposing of positive donations, cleaning and decontaminating the laboratory. For these we have to have SOPs, and here is the SOP which we have in our department for HIV testing, for HPS-AG testing, for malaria antigen testing, for HCV testing, syphilis testing, and NAT testing. These are the SOPs we follow here in our department. Then the second point is design forms and checklists. Blood bank should develop checklist or worksheet for each assay, detailing all the required actions in a correct sequence. After the screening, the completed worksheet becomes the quality record of that batch of testing and should complete the quality circle, providing traceability. Now, essential components for quality control. The quality control in TTI lab denotes the consistent measures undertaken for each TTI assay to ensure that the test should work accurately as per the limits of the test to provide valid and acceptable results. The elements are internal QC covering the reagents and techniques, assessment of specificity and sensitivity, batch pre-acceptance testing of new batches of kits, external quality checks, and external quality assessment. So the important points for consideration prior to use of kits and performing the assays. We should keep these points in mind. It should be mandatory to use licensed approved kits from the Government of India, and we have to use the kits before the expiry date. We have to follow strictly the physical parameters as incubation time, reagent concentration, temperature range mentioned on the test insert. So we have to follow the steps whatever is given in the kit. Kits and samples should be brought at room temperature before use. Bells of the plate should not be touched with micropipette tip. This is in relation to ELISA. Always use tips compatible and recommend with the micropipette. Controls and unknown samples should be treated in similar manner. Reagents from one kit should not be mixed with another. This is also important. So, moving on to internal and external controls. Each test must include one full set of controls that yield results within the limits of standard for acceptability and validity. Any test run not having at least minimum number of controls within acceptable range is invalid and must be repeated. So what are internal controls? Internal controls is also known as kit controls. So it will be provided with the kit. It should be used with the same batch only. Set of controls provided with the kit. So the company will be providing us with both positive and negative control kits, and these do not, but the thing is these do not detect any minor deterioration of the kit. External control. So this external control, where we can get it from? We can get it from national reference centers commercially as control panels, and this can also be prepared in-house from reactive and non-reactive blood bags. But the advantage is these detect any minor error in the assay performance. Whereas internal controls, they do not detect any minor deterioration, and external controls can help us serving that. So how are we going to prepare the external controls, in-house external controls? We are going to take a high titer seropositive serum or plasma. We are going to retest it again with another kit sample, another kit. We are just confirming it if it is positive or not with another kit. Then we are going to inactivate the sample at 56 degrees Celsius for 30 minutes. And if we have taken the plasma, we can convert it to serum by recalcifying it. And because plasma is unstable, as we know, we are going to take this and we are going to make serial doubling dilution of the sample with the seronegative serum. So we are going to make the double dilution here. In the first two tubes, we are going to take 200 microliters of serum, of the positive serum. In the first tubes, we are going to take 200 microliters of positive serum, and instead of adding normal saline, we can add normal non-reactive serum. In the tubes 2 to 10, we are going to add normal non-reactive serum, and then we are going to do double dilution to this. So here it is recommended to use normal non-reactive serum rather than normal saline. First two tubes, seropositive serum we are going to add, and in the tubes 2 to 10 we are going to add non-reactive serum, and we are going to dilute it. So how we are going to find the suitable dilution? Test each dilution in the same run for the particular assay for which QC is being prepared. Note down the ODs. Calculate E ratio. We are going to calculate E ratio by sample OD optical density divided by the cutoff optical density, and we are going to get a sigmoid curve for this. I'll show the curve. An appropriate dilution between E ratio 1.5 to 2 in case of indirect or competitive ELISA and 0.7 to 1 in case of sandwich ELISA should be selected from the linear position of the curve as the borderline control. So this is our sigmoid curve, and here is the cutoff. Negative control is in the bottom and positive control is in the upper side. And again, as said, this is the sigmoid curve, and E ratio should be between 1.5 and 2.0 for indirect or competitive ELISA and 0.7 to 1 for sandwich ELISA. So how we are going to interpret the results? So sample ODs at or above the cutoff value. Whichever is above the cutoff value of 1, it is going to take as, we are going to take it as reactive, and sample OD whichever below the cutoff value, we are going to take it as non-reactive. But if it is in between, what we are going to do? It is called as gray zone samples. Those below the 10% of cutoff value, only between the 10% of cutoff value, it comes under gray zone, and these should be repeated in duplicate. So if one or both above cutoff value, we can term it as reactive. If both the values on repeating the test, if both the values are below the cutoff value, it should be termed as non-reactive. This also will be included with the kit which we get. So in the quality control, there is a line mentioned as absorbance of all the positive control should be greater than or equal to 1.0. And at least 2 or 3 negative control should be less than or equal to 0.200. Even the negative control mean should be less than or equal to 0.2. So this also will be included in the kit. So how we are going to standardization? How we are going to do standardization of the quality of external control? We have made the external control, we have diluted the sample, we have checked for the results. Now how we are going to standardize it? The external controls must be standardized by intra-run and inter-run reproducibility. they are tested at least 3 times on the same test run. So by this way, we will produce the intra-run reproducibility with the same test. This exercise is then carried out on test runs on 3 consecutive days. By this way, we can get the inter-run reproducibility. If it is producing the same result again and again on the same day and on 3 consecutive days. So by either of these methods, the variation should not exceed 10%. Then our test is standardized. So what is homogeneity or repeatability? This also we should know. Once the batch that has been dispensed into smaller volumes, a specimen from each of the allocates must be tested to ensure that each allocate will produce the same results. Then the batch is reproducible and homogeneous. We have to get the same results. By how much of our time we are doing, we have to get the same result. Then the batch is said to be homogeneous and reproducible. So how we are going to select? We are going to select randomly 10 to 20 allocates as per the lab policy. We are going to test each of them in the same day or 2-3 days as per lab policy. This is again the same reproducibility, intra and inter-run reproducibility. So moving on to statistical analysis. Now we have got some values and we are going to use some statistical analysis for that values. This is again important for monitoring the QC in TTI. We have to need at least 20 points for this. That is mandatory, which is obtained over a 20-day period. Each day one value we are going to take to calculate the mean, standard deviation, and we are going to develop a chart which is Levy-Jennings chart. So what tools we want for this data management? We have to have some basic statistical skills and we have to know how to use graph paper, calculators and spreadsheets. So how we are going to set the target values? We have collected the optical density from the graph which we have plotted for the controls. And we collected optical density values for control for each assay run. We have collected cutoff value for each run which will be given in the kit only. And we are going to calculate the E ratio. What is E ratio? This is the ratio of OD to cutoff value, optical density to cutoff value. In non-competitive ELISA, we are going to divide the sample OD value by the cutoff OD value. Whereas in competitive ELISA, we are going to divide the cutoff OD by the sample OD value. And we are going to calculate the mean. Mean is the sum total of the E ratio by the number of reactivity. This way we are calculating the mean. And standard deviation, again, it is also, we have a formula for that, and it is calculated as comparison of each of the individual values of E ratio with the mean to find out the deviations from the mean. If for example E ratio is x1, then the deviation will be x1 minus x, which is expressed as small d. The deviations are then squared. These square deviations are added and expressed as sigma d square or sigma xn minus x the whole square. The test is then divided by the number of readings. So this is the formula for standard deviation, and we are going to calculate the coefficient of variation also by the formula CV is equal to standard deviation into 100 by mean. Any CV less than 10% is considered as an indication of a very little variation. So now we have calculated the mean and standard deviation, and we are going to see how we are going to select the assays. So it should be sensitive and specific. Both sensitivity and specificity should be the highest possible values. So as we know, sensitivity is the probability that the test will be reactive in an infected individual. The sensitivity of an assay is therefore its ability to detect the weakest possible positive sample. Whereas specificity is the probability that a test result will be non-reactive in an individual who is not infected. The specificity of an assay is its ability not to detect false or non-specific positives. So how we are going to calculate the sensitivity and specificity of an assay? So we are going to take the true positive, true negatives, false positive and false negative. Sensitivity is the ratio of true positives by true positive and false negative into 100%. Specificity is the how we are going to get? We are going to get it by dividing true negatives by false positive and true negatives into 100%. So the sensitivity and specificity, both of them are inversely related. So if sensitivity is increased, specificity decreases, and if specificity is increased, sensitivity will be decreased. So predictive values, we should know what is predictive values. It is another way of looking at the performance of an assay. What can be expected from the assay? The positive predictive value and negative predictive value are measures of the actual performance of assay in blood bank. Positive predictive value is the probability of a positive test, positive result being truly positive. A negative predictive value is the probability of a negative result being a true negative. So positive predictive value is given by the formula true positive by true positive and false positive into 100%, and negative predictive value is given by the formula true negative by true negative and false negative into 100%. So how we have selected the assay also. We have the standard values also, mean and standard deviation also we have. Now we have to see how we are going to use those. For that we are going to plot these values in a Levy-Jennings chart. So we are going to plot control values of each run, and we are going to monitor it over time to evaluate the precision and accuracy of repeated measurements. The closeness of measurement to the true value is indicative of the accuracy of the assay, and the degree of fluctuation in the measurements is indicative of the precision of the assay. We are going to not just plot, we are going to review the charts also. So this is our Levy-Jennings chart. So it is an invaluable tool in any TTI that is using ELISA as the screening test. As we already know, we need at least 20 points, which is taken over a period of 20 days to define our mean, standard deviation and our range. We have calculated the mean, standard deviation and range, and now we are going to take the chart and label the x-axis as the time period for the run, day 1 to day 31, and we are going to label the y-axis as the control values, that is mean and standard deviation. So in this we are going to have the mean in the center, and on both sides of the mean we are going to have our standard deviation, +1, -1, +2, -2, +3, -3. So if for example our mean is 90 and our standard deviation is coming as 5, so the ±1 standard deviation will be around 85 to 95, and +2 standard deviation will be 80 to 100, and +3 standard deviation will be 75 to 105. That will be our range, and we are going to plot the graph with the mean and standard deviation which we have. So scale and label the y-axis from lowest to highest expected control values so that the mean is located at the center of your graph. SD is the numerical value applied in an increasing or decreasing fashion on either side of the mean, which is on either side of the mean, to donate +1, +2, +3 numerical values. Write the numerical values obtained for these next to the correct label on the chart. Now we are going to draw lines for mean and standard deviation, and we are going to plot it. So in general, the ±2 standard deviation is the criteria for the limits of acceptable range for a test. So when the QC measurement falls within that range, the range is ±2 standard deviation. If it falls between these two range, then it is okay. Then there is a 95.5% confidence interval that the measurement is correct. If not, the test for that run is not valid. And in what other cases the test will be not valid is if the standard deviation is beyond 2 standard deviation, or if one external control beyond 3 standard deviation, or external control values exceeds standard deviation in 2 consecutive tests. So when will this occur? Only at 4.5% of time will a value fall out of range due to a chance. More likely that too will be due to an error. Over 4 to 7 days, if the E ratio is within ±2 standard deviation but shows gradual increase or gradual decrease, which means either kit or the operator isn't faulty. So here this is the mean which is in the center, and the standard deviation are plotted on either side of the mean. This is a normal graph because it is like between plus and minus standard deviations. So what is the application of this control chart? It highlights the outliers, which is values outside ±. Yeah, that was not into the range. In -3 standard deviation, one has come. So now we will check how what we will do if it is more like this. I mean, what we will do if it is beyond the range, we will see that also. So what is the application? It highlights the outliers, that is values outside ±2, it highlights, and it reveals batch to batch variation, it reveals operator to operator variation. So what is the scope of this chart? It helps us in seeing the systemic variation, random variation, lot to lot variation, and day to day variation as well. So what is this systemic variation? Here we need to know two terms, shift and trend. So trend is nothing but a results in gradually the change will be gradual in either direction, indicating slowly changing parameters. So trend is something which is going to happen very gradually. It can be either due to deteriorating reagents, failing of the equipment. Whereas shift is something which happens very fastly. Either it falls abruptly or sharply on one side of the mean, indicating a major change has occurred. So see here, in the shift, control values of 6 consecutive runs fall on one side of the mean very abruptly. There is a fall which is very abrupt. This is shift. So the reasons can be switching to new lot of kits, new reagents, changes in incubation temperature, new technical hand. Whereas trend is 6 consecutive points distributed in one general direction, and also it is slower. The possible cause are deterioration of reagents, deterioration of light source, gradual deterioration of calibration, and slowly faltering equipment. So these things we should know about the systemic variation, shift and trend. So now control values if it indicates a problem, which we will analyze with Westgard rule. Okay. So if it is between plus and minus 2 standard deviation, it is a normal graph and whatever test we have done was correct. But now if it has violated something, what we are going to do? So there are some rules for it basically. I have not taken every rule, I have taken just 6 rules. This is rule of 1 2s. Here there is one time violation over plus 2 standard deviation. One time there is a violation over this plus 2 standard deviation, and for this we can actually perform the test. Like the performed test is actually right only because there is just a slight variation, that too with only 1 plus 2 standard deviation. So this test is actually okay only, we don't have to repeat the test again completely. Here this rule violation is 1 3 years rule is one time there is a violation in 3 standard deviation. This also it is okay, the test is fine, we don't have to repeat the test. One time there is a violation in the 3 standard deviation. This also the test is fine. Here 2s rule violation. Here also 2 times there is a violation. There is a violation happening in 2s, 2 standard deviation. Here also the test is fine, we don't have to repeat it. But we have to make sure the next day also this graph doesn't come. The graph next day at least the graph should be within plus or minus 2 standard deviation. For one day this is okay. This we can continue. The other 3 rules are rule 4s. So in this there is a complete shift from like 4 standard deviation have completely gone at a time from plus 3 standard deviation to minus 3 standard deviation. There is a abrupt rise and fall in the graph. So here this we have to repeat the test. This R4S is there is a complete entire 4 things it has blocked and it has directly come down and went to the upper side. So here we have to repeat the test, we have to stop it and we have to repeat the test if we get this kind of graph. And rule 10x rule violation. Here it is we are going to get small points everywhere within a set of 1 standard deviation, within a set of some 1 or 2 standard deviation, but we are going to get n number of points here. So we are going to get n number of points within the same 2 standard deviation. N number matlab 10, at least 10 points we are getting. So this also we have to repeat the test. And the rule is 4-1s rule. Here in between 1 standard deviation and 2 standard deviation, we have some 4 points in between. We have plotted the control values, and in between the 1 standard deviation and 2 standard deviation, we are getting 4 different points. This also we have to repeat the test. So these are some of the violated rules from Westgard. If on plotting the control value, we are getting some of the violation, and we can decide whether we have to repeat the test or we don't have to repeat the test. For simpler 1 variation or 2 variations, it is okay, we can proceed with the test. But if there are more violations, then we have to repeat the test again. So systemic variation is over. Now moving on to random variation. Random variation is evidenced by observance of one result significantly different from other results without any pattern. As such, systemic variation we have some pattern. For shift and trend we have some pattern. But random variation occurs very randomly. It doesn't have any pattern also. It could be due to mislabeling, data entry, sample mix-up, errors in addition of samples to the plate, interchanging specimens, poor prepared precision, lack of equipment maintenance and calibration, ELISA reader which is not calibrated, poor technique as inconsistent washing, sudden change of staff or kit used in the blood bank, lack of periodic training and following the SOPs. So now we have seen the variations, systemic variations and the random variation. So troubleshooting, if whatever time we are going to get some troubleshooting, why there will be a troubleshooting? In pre-analytically, it can be due to hemolyzed sample, which we receive, grossly lipemic samples, repeated freezing and thawing, contaminated samples and reagents, improperly stored, expired and deteriorated reagents. During the test, analytical sample, in the analytical process, what and all we can face is pipetting errors, improper incubation time and temperature, improper washing procedure, equipment malfunction, glove powder. It can be even due to the glove powder and calculation errors. Post-analytical, that is when we read the assay, what we can see is there will be no color formation in the entire plate, which can be due to reagent which is added in the wrong sequence. These steps should be followed correctly. If not, we can get a thing like this. It can be due to inactivated plate, it can be due to inactivated reagents also. And what if we get a high background color like this? Everything will be colored. It can be due to washing errors, because when we wash, everything will, like the substrates can go, but if the washing is not proper, this can occur. And contaminated wash buffer, even on washing, if the buffer is not proper, also this error can occur. And waiting too long to read plate after adding stop solution. Substrate incubation should, if it is carried out in daylight, that can also cause this problem, because it should be ideally incubated at dark. Incubation should be kept. If it is not, then this problem will occur. And in dirty plates also. Another two effects I want to say. One is hook effect. This is like a false negative report actually. Ideally, whenever there is an increase in signal, there should be also be a linear increase. Till this side, it is okay. Whenever but as the concentration of the analyte, that is the substance which we want to measure, increases above a certain point above this, the system itself gets saturated and the signal begins to decline. So till here it is okay, it is taking it correctly. But after some point it gets saturated and it deteriorates. So they are saying this similar to prozone phenomenon, which is low measurement of analytes which are otherwise present in very high concentration. Analytes are actually present in high concentration, but the system takes it up as low concentration. It results in a false negative report and it resembles a fish hook. That is why it is called as hook effect. And how we can prevent is we have to dilute the sample so that it can be prevented. The one more effect is edge effect. So wells at the edges of the plates show higher absorbance. So there will be, it will come like mostly it will be coming positive in the edges of the wells because due to higher absorption, and dependent on the relative temperature of surrounding causes evaporation in the circumferential wells. How we can avoid it is we should avoid stacking of the plates, and we have to use during incubation. We are going to keep for 3 incubations. In those 3 incubations, we have to make sure we are using a seal foil for incubation. Documentation, this we already know. We have to include the sample collection date, sample test date, identification of test run in which each sample was included. We need to know in which lot it was processed, the manufacturer, product number, lot or batch number, and expiry date of the assay kits used. The name of the operator and the supervisor should also be known. The assay procedure, the results obtained, the preparation of any reagents or buffer should also be mentioned in the documentation. And the temperature monitoring records for the laboratory, incubators, water baths and refrigerators used for storage of assay kits or reagents. Maintenance and calibration records for the equipment used should be done periodically. Records of disposal of any positive donation should also be mentioned. How we are disposing the positive records, that also should be mentioned. So this is a sheet which, this is the documentation which Blood Bank Technical Manual has given. Here, this is the plan for ELISA microplate. And this on the right side, this is the discard log. This is how we have to discard it. Like we have to maintain the discard register also. Last but not the least, the training of all staff is the most important thing. The important part of quality control is training of all staff on SOPs, QC and calculation of statistical values. And we need to know about the plotting of LJ charts. It should be an ongoing process with documentation. These are my references. Thank you.